We were just waiting for the hall to get a bit more full and start off today's sessions, which are related to the 30-meter telescope project, sponsored and supported by the 30-meter project, 30-meter telescope project. And as you may or may not know, we will be here all through this week till the 9th, which is Sunday. So we started yesterday and we'll be here till the 9th, doing a repeat of all the sessions that will happen today. So which include a talk, special talk, which I'll be delivering right now on this topic. And then we'll have some live demos of optics experiments. So you know optics, which deals with light and the way it interacts with things around us, especially also properties of light, which are able to give us more information about things far off and close by. So that, of course, will not be as boring as I made it sound just now. It will be a skit with a famous personality that you know from history of science, and that personality will appear on stage, and then we'll have fun with that person also thinking about all the new things which have been invented after he has passed on, right? So it will be lovely to see the reactions and also to see the hands-on experiments which will be done on stage with lasers and LEDs and things like that. That's the second attraction. That will be at 2 p.m. every day. This talk will be at 10 a.m. every day. And in between, you can always visit the telescope making corner inside the science center in the main building, where you know there are lots of dinosaurs outside as security. So you can go inside and have a look at the options that you have if you want your own telescope, right? Whether you want to make it or you want to get some from somewhere, or you just want to see a telescope, the kind that one of them is shown here. So you're welcome to do all this while you're here. I think most of you are from the workshop which is going on here in the Science Center. But other than that, if you want to come otherwise, because you may not have got time till now, you should definitely visit the exhibition which is going on, and it's at the right at this at the start of the Science Center entrance. Tell your friends, other family members, the schoolmates, whoever can come here should be able to enjoy this through the week. Alright? Okay. So we're ready to start off and go into the world of large telescopes. Right? And it is as I said, being supported by the 30-meter telescope project. You'll notice in these graphics on both sides of the hall that this exhibition called Vigyan Samagal, it basically combines expertise from there's 7 mentioned here. So 7 projects which have Indian contribution. These are not just any projects like a college project, etc. These are mega science projects with say 1,000 crore rupees investment or more kind of projects. Okay. And of course they're not just mega because we're spending a lot of money on them, but they're mega because the achievements will be mega. Okay, they take our level of understanding of the nature, the universe, a big step ahead. Okay, and one of them, in fact, even is attempting to create a new source of energy, controlled energy, which we have explored till now, but it's not yet been controlled on Earth. So a lot of exciting stuff, and in that you will notice the 30-meter telescope is something which will be related to astronomy. It's looking at the sky, space, and it will give us new knowledge. So I'll explore some of that in this talk, but I'll also ask you to go to the exhibition and find out more from the volunteers and the panels there, the posters there. Well, if you want to know about telescopes, you have to tell me, are any of you interested in astronomy? Okay, lovely. So that's a big number. And so how much astronomy have you done till now? Anything is fine. Anybody want to share one person? so that we can have a conversation instead of us just giving a talk here. We can talk together. Anything you want to share which you did as part of what you understand is astronomy? So that's fine. So that's why I want the ball to start rolling. So she's read books about astronomy, and what else? Have you actually looked at the sky? Which you definitely need to do. I love food, but I can't just read recipe books and say I love food. I need to go and eat somewhere and taste it also, right? So yes, do read books, lovely information sets, but also explore possibilities of looking at the sky yourself and furthering your knowledge of how astronomy is done, at least at your level. And then, of course, you'll have some inspiring things shown now, which you can aspire to be part of later. So astronomy is basically a study of things which are outside the Earth's atmosphere, away from the Earth. Okay, and most of them are very far away. Some of them are close by, like the moon, some asteroids, meteorites, etc. But most of the things are really, really far away. Okay, and the difficulty which comes because of that is that we cannot use any other sense other than our sight. Right? So none of us has ever tasted the moon or smelled how it is there, right? So because it can only be seen, things can only be seen. Okay, so light is the only carrier of information because that's how we see things. And so I mean, human beings have been doing astronomy for thousands of years because the sky is free for everyone to see, and earlier they had even less distractions compared to these days when we have lots of serials coming on at night, etc., or movies. But all those people were limited by their eyes. They were limited to seeing the sky with their eyes. Around 400 years back, there was a revolutionary step where somebody combined something called lenses, okay, glass pieces shaped in certain ways, and they noticed that things could become, they seemed bigger in size. Okay, when you saw through that combination of lenses, maybe if you put them in a tube, it seemed even better, the image. And then that was called a telescope. Okay, the idea being that I can scope is seeing, and I can see tele means like telephone, television, so I can see far off. Okay, so it's a telescope which can make you see things which are far off. Alright. So that was one of the aims for which telescopes were made, but then what far off things could people think of? They would think of birds or things, scenes far off, or maybe checking whether some enemy army is coming towards you from the horizon, right, and getting early information. However, one person, his name was Galileo Galilei, he thought, let me turn it even farther and try to, let's say, look at the moon, which seems quite far. So at that time, people didn't have a distance estimate of how far is the moon, how far is Mars, Sun, etc. Right? So they even believed that everything goes around the Earth at that time. We're just talking 400 years ago even. Even at that time, we believed that everything goes around the Earth. So we didn't have enough information. And that moment where the first telescope was used revolutionized things, and it changed our perspective of looking at the world, looking at our place in the universe. So that's a philosophical step, but let us see what practical purpose the telescope was used for by Galileo and subsequent astronomers. So telescopes are things which can be, which aim to show you things better than your eyes can show them, right? So the three main aims of a telescope is to look at distant objects, but not just look at them, make them seem bigger, okay, brighter, and sharper, showing more detail, okay, not sharpening of a knife. So they, compared to what they appear to the naked eye without any telescope. Alright. So the three factors here are, all these three effects actually, which the telescope produces, are dependent on the size of the telescope. Okay, and therefore, when astronomers talk about telescopes, they usually refer to the size first, and then they go on to saying what color it is or what kind of stand is there or something like that. So the size is one of the most important factors, okay, and also the shape, curvature of whatever is being used inside, right? Bigger, brighter, sharper. Bigger is because of what we call magnification. The image which is produced by the system, the telescope, is bigger in size compared to what our eyes only would make, right? So I can see things magnified. However, that also restricts me from seeing all the things. So right now I'm looking at all of you, and I can do like this, and I can see all of you at one time, right? But I don't see much detail. You seem very small being back there, right? A telescope right here would allow me to see you very well. Maybe your face will be the size of your face, but then I'll not be able to see the rest of you, right? Because I'll be only able to see one small area but magnified. Right? So this is a compromise that I make. I see a small area, but I see things bigger. Okay, that's a compromise. The size of a telescope, usually these telescopes have something which collects light first, which basically interacts with light first. And maybe let me take you to an example of kind of telescope. So this is called a refracting telescope, which has a lens on it. Okay, this is well known to you that lenses are used in telescopes, and here in fact is a kind of telescope which Galileo had also used at his time. Very similar, not the same components, but there is a lens, this first big lens that you see, and this grayish patch with arrows in it, let's say that is the ray of light. Those are rays of light coming from far off. Okay, far off objects seem to give out parallel rays. This is something people interested in physics would understand, but even if you don't want to dwell on that, these are the rays coming from far off. Okay, so they will be parallel like this and come in a beam, let's say. So this is the first object which interacts with the light coming from far off. Okay. If you compare it to your own eye, then there's a lens here, right? In your eye, there's a lens here. So that is the first object which interacts with the light coming from far off. Right? So, so this is called the primary element of a telescope. Right? The primary element is the first thing which interacts. So you can see it's called the primary lens. So the size of the primary matters a lot. Okay, and that's what I was saying. When we talk about sizes of telescopes, we are referring to the primary, the first element, size. Okay, and that kind of defines the size of the whole telescope itself. Right? You see, I don't have any part which is kind of bigger than this. So I have to enclose this, let's say, within a tube, this whole system. So that kind of governs how big the telescope, the whole telescope would be. Right? Because it's not just the lens, there's other systems. There's another thing which we need to know is these primary systems, the optic systems, they have something called a focal length. Okay. And what is this focal length? You will notice that this lens actually takes this light which is coming from far off and it changes its direction. Okay. So light which hits this edge of the lens gets deflected into this direction and reaches here. This ray that is reaching the edge of the lens is diverted here and reaches here, and there is a point where this ray and this ray both meet. Okay, and subsequently all the rays in between, they also are diverted, but they don't meet somewhere here. They all tend to meet here. That's the property of a lens, and this is because there's a there's a difference of thickness at various places on the lens, right? And that's why a lens can deflect all the parallel rays to the same point. This is called focusing. Okay, and have you ever tried taking a magnifying glass and in the sun and trying to burn a leaf or a page or something like that, paper? Okay, I know that's playing with fire, but if you can do it in safe environments, not near your bookshelf or something, but take it on your rooftop or somewhere on the ground and do it safely. It's a fun activity. Don't put it on your hand, put it on the paper only. But that's what you're doing there. The lens is focusing the light of the sun onto a point. Okay, and if you could actually see the light going, this is how it would look like. Right? So it's like a funnel. You put all the light here, and then this thing takes the light and puts it into a small narrow place. Okay, a funnel which is used to pour, let's say, some liquids into a bottle. It has a wider top and a narrow bottom. So all the stuff that you put on top can slowly go into the narrow bottom and goes into the bottle. Here, instead of going to a bottle, it can go to a point. Okay, and what happens after that? What happens? What do you think happens after that? After the light ray, it hits here, it goes in this direction, and it reaches here. What happens after that? No. Okay. That's. I'm just asking about this ray. What's happening to this particular ray?
Becomes dark.
Right. So just think of this. The answer is very commonsensical. So and very simple. So many questions in science have simple answers, and they lead to some effect, which is really nice. Yeah. So as you said, yes, it's very simple. Why would the light stop here? It keeps going. There's nothing to stop it there. It's just a point in space. So like in air. So it keeps going this way, right? And this light keeps going this way. However, and they don't interact. When they come to that point, they don't talk to each other or stop for a chat or something. They keep going in that direction. Only that direction has changed. That's what the lens has done. That's all. Okay. So they keep going. So now, when after this point, if you catch the light somewhere, they will start becoming another bigger cone. Okay, another part of another cone. But as you said, since this light has gone this way and this light has gone this way, the image, if you take it on a screen, would be inverted. So that's an effect of it, effect of the property of light, that it goes in straight lines and doesn't stop unless it is absorbed or deflected by something. Okay. So this lens system does that. So primary lens has a diameter and something called a focal length. This focal length depends on what kind of curve its shape is. Okay. This distance from the center of the lens to this point where it can focus the light to depends, is called the focal length, and it depends on the curvature of the lens. So we can change the curvature and change the focal length as well. Right? So these are a few things we should keep in mind if we are studying about physics and optics. Now the ingenious thing people did was that they noticed that if I use a lens, it changes my light's direction. So it's like a funnel. So if my eye is very small, and if you notice, actually, just look at your friend's eyes, each other's eyes, the area through which the light enters your eye is only about not even 1 centimeter. It's 0.7 or 0.8 on an average human being centimeters. Okay, so that's a very small diameter. It's a tiny circle it makes. Right? Now, if I had bigger eyes, I could probably see things brighter because I would get more light. I could probably see in the dark also. However, that cannot happen. And therefore, what we do is we use a funnel. Right? So let's say if you want to collect rain water in the same bottle that we had to collect water, and you put a funnel on it. Right? So you take the bottle separately, stand there for 15 minutes, you'll hardly get any water. You put a funnel on it, stand in the rain with the bottle, and you'll collect much more water. Okay? Why? Because the whole area of the funnel is collecting water and putting it into the bottle. So what we did was we made a light funnel. Okay, we made a light funnel which is called which has a lens, let's say, and it collects the light and puts it to a point. But the point is no use to me because I want to see a point does not give me any information. It's just a collection of light. My eye also has a lens, and to form an image on the retina, it has to have parallel light. You understand that? So this parallel light is what is coming to my eye also. Right? If there's no telescope or lens in between my eye, let's say, just light coming from you all, right? It's almost parallel light coming to my eye lens, and that is causing an image on my retina. It's very similar to this kind of lens, and this could be my retina where the image is formed on my cones and rods. So if my eye needs parallel light, and this lens is giving me only a point here at one place and then again a diverging light, I need to make that light which is more than what my eye could collect. It is the amount of light has increased, but the usability is not there right now. So what we use is called the eyepiece lens, which converts this light into parallel rays. Okay, so lenses have this other property also, that if a lens can focus light, parallel light to a point, then they can also do the opposite. If the light is coming from their focus, they can make it parallel. Okay, so ulta bhi karte hain. So this eyepiece lens basically makes the other thing happen, and then this eyepiece, this parallel light is where in this parallel light is where you put your eye and see. Okay, so a telescope will this lens will not work as a telescope. You need an eyepiece lens as well. Then it's a complete telescope. Right? That's why it's a system. So this is the eyepiece, and this is the primary. Okay, so now this diameter, as I just told you, if you increase this diameter, the amount of light you collect increases, and the area increases. Can any of you guess if I make this? If this lens is, let's say, 1 centimeter, no, 1 centimeter is too much, too less, 10 centimeters in size. Okay, how much is 10 centimeters? So, show me with your hands. Okay, your small rulers are probably around that size, right? Okay, so this size, let's say, and now I double this size. Okay, I make it double. How much does the area change? If you studied geometry in your class, then can you tell me how much does the area of the circle change if I make the diameter double or radius double? Okay. Does everybody agree with her? Can you tell me why? Lovely. Yes. So compared to 1, the final area is 4, and lovely answer. So she knows her geometry very well, and that is what is being used here. You see, I just double the diameter, and the area becomes 4 times, and this whole area is contributing to collecting light. Right? It's not just the radius or diameter. Okay? So therefore, every time I increase the diameter, I can change the area by a large factor. In fact, by 2 it changes to 4 times the area, and if I increase the diameter by 10 times, can you guess how much the area will increase by? 100 times, right? Just imagine 100 times more light, right? If I can just go 1000 times, 1 million times increase in area, right? Just an amazing feat if you can do that, right? So yes, so that's the kind of wonders we can do with telescopes, and therefore the diameter is very important for brightness. Okay, but it is also important for the other things that I told you about. What were they? That it of course makes it look brighter, but the eyepiece and the eyepiece and the main lens, or the primary as we can call it, also together contribute to what is called the magnification, the size increase of the image. Okay, because you see the image will be found after this focus somewhere. So what this contributes is that if you know the focal length of this lens, if you know the focal length of this lens, the ratio of them, the division, if you divide this by this, that gives you how many times bigger will be your image which is formed. Okay, this is a little more advanced optics, not just ray diagram, but you can actually calculate what is the magnification that you want and then use an eyepiece accordingly. Right? This lens you cannot change the focal length of in an ordinary telescope, but this you can change. So you say that, okay, this has a focal length of 10 centimeters, and I want to see things which are 2 times bigger than what they normally see. Then I can have this as 5 centimeter long, right? And as you go lower and lower, say I want to see things 4 times bigger, then you use 2.5 centimeter focal length, right? You just use 1 centimeter focal length, then you get 10 times increase in size of the image, right? So that is another factor that is there, which the eyepiece lens then contributes. Okay, so bigger, brighter, and sharper. This is a slightly advanced thing, but the size of this also allows you to get more details in the image that you are seeing, right? So it's not useful to see just a fuzzy object, although it's looking big and fuzzy and bright, but there's no details in it, right? It's no use looking at such things. We don't get much information. So these two elements combine together to give you all three effects. That is what Galileo thought. And then all the subsequent people after Galileo, they started doing astronomy with such telescopes. They started increasing the size of their primaries, okay, of such similar lenses. And they realized after a point that we can't make lenses very big. Can you guess why we can't make lenses very big? What is the largest size lens that you have seen? Those who were here yesterday, please do not give away the suspenses, but yes, okay. What is the largest size of a lens that you have seen? Yes, when did you see it?
In the TV when I saw an episode of Telescope.
Okay, yeah, so that's some specially made lens. But have you seen yourself? I try to ask questions which are related directly to you, rather than I mean, on TV everybody can see the largest telescope, but what is the biggest telescope that you have seen? You is more important, right? In your life, who is the most important person? You are. I mean, whatever you say, my parents are important, somebody is important, Nanaji is important, but finally it's only you that has to live the life. Anyway, so if you just look around, I think maximum size of lens that you might have seen is this or this in some magnifying glass at home, right? And we don't come across big lenses too often. Not even spectacles, binoculars भी छोटे होते हैं. Camera lenses हैं, they are also not too big, they're about this size. The difficulty is that you have to have perfectly shaped glass, which is completely transparent, clear, doesn't change its shape or characteristics, okay, and is free from some things we call aberrations. It is very difficult to make in glass, right? And if you do want to make it, then the cost increases a lot, really a lot, okay? Because nobody does that, so you have to do special arrangements to make it. And how do you make these lenses? You have to actually grind them. You cannot cut a glass piece like that. So you have to slowly grind, and it takes a long time to do that. Therefore, it's a long, patient procedure, and nobody wants lenses that big. So astronomers got frustrated because it was a long-run process, and they got tired, and they said, okay, fine, I understand there's a need for bigger telescopes, but can I find a better, smarter alternative? That's what scientists would think like. Okay. And somebody did find something. So there's a person called Gregory, and also somebody called Newton. They came upon ideas around similar times at a similar time, and Newton in fact invented a very simple telescope called the Newtonian Telescope. Right? And this one, in fact, here that you see is a kind of a Newtonian telescope. So what he did was, instead of a lens, what he used was something called a concave mirror. Okay, a mirror which is curved inwards. And lo and behold, what people had already discovered was that a concave mirror also diverts light in a way similar to the convex lens. Right? What was the lens doing? It was focusing it to a point. What does a concave mirror do? When light rays fall on it, parallel light falls on it, it also diverts them in a way so that they will meet at some point, which is called a focus length. So it has a focus, it has a focal length, just like a lens. Alright? So just take out that lens and put a concave mirror instead. And now I will ask you, what is the biggest mirror that you have seen? Okay. Every day you see mirrors be bigger than any lens you have seen, right? While brushing your teeth maybe. Yeah. Those are of course flat mirrors. We have to make concave mirrors, so slightly slightly harder process than just making flat mirrors. And so there we have an option which is cheaper and easier to make compared to a lens which needs to be completely transparent, etc. A mirror doesn't need to be transparent. You just have to have a curved surface and make it shiny on one side. That's all. And then it will start reflecting light. However, what is the problem? The problem here is that the lens can let the light pass through. A mirror cannot. And so now mirror will be deflecting it backward, reflecting it, sorry. So reflecting it backward. Now where will you put your head? There is a mirror here, light should be coming from here, and now you want to see it from there. So your head will block the light. Okay. So what the ingenious idea was that, see, as the light comes here, the cone reduces in size. The diameter of the cone is reducing. So what Newton did is, ingeniously, he found a place, a sweet spot, where he could place a small flat mirror. The small flat mirror is much smaller than your head size, right? And that also covers the size of the cone which it forms here. And then from there he deflected it at 45 degrees in a perpendicular direction to the light which was coming. And here he made a hole in the wall of the telescope and put an eyepiece lens. That's all. So he calculated things such that the focus, instead of being here, is shifted here by 90 degrees. Okay, clever thing, right? So he did that, and it quickly went from here to here, where you could easily put an eyepiece lens and take it down, take the light down. Do you see a problem here in using the telescope? Sorry? I mean, you can always turn this upward also, right? That's not the main problem. Well, some people say it's a problem that I am seeing things. Earlier I was seeing things in the same direction. So if the star is here, say, let's say, so I look from this direction and I'm pointing in this direction. I take my telescope and point it like this. Right? What about here? The star is in this direction and I'm looking in this direction. My eye will be like this and the object will be here. So you may find it difficult to, let's say, find birds or something like that if you look like this and the object is here somewhere. Okay. But then you can make it a habit. Slowly, you develop a habit and get habituated. And this is better because now you can have bigger and bigger mirrors. Mirrors are easier to make compared to lenses, and you can have them bigger and bigger. Okay, so that's the advantage you get. In fact, I don't find this as a disadvantage for astronomers whose main objects to study are up there, not on the ground. Right? And just imagine having a telescope like the previous one and looking at it like things like that for hours. Right? Now here what you are doing is you are looking like this. Your neck is not strained, you are not doing a yoga pose, you are looking like this and you can see the whole sky up there. So it's actually a convenient thing rather than a disadvantage. So that's a reflecting telescope, a Newtonian telescope. Of course, some person said, no, I still want it to see in the same direction that I am pointing the telescope. So then they said, okay, let's make a hole in this mirror. So here the mirror is complete. It's very cheap to make. You make the mirror and just attach it and put a flat mirror. The other person said, no, I want a hole here and then I will put a mirror here which will deflect it in this direction. Okay, and then I will put the eyepiece here. Perfectly fine. You have your wish. And we had the Gregorian design, which later was modified by Cassegrain, another scientist. And so this is the latest Cassegrainian type telescope, okay, which is reflecting. So it uses reflection rather than refraction of light, and it gives you the telescope looking in the same direction as the object is. All right. So these are the three, basically two types of telescopes: reflecting and refracting. Now I have already told you that reflecting and refracting telescopes both use a primary. Okay, one of them is a mirror, one of them is a lens. Lenses are difficult to make in a bigger size, and so we try not to use them. Okay, and we are going to reflecting telescopes. So this forms the base of the rest of the talk, which is about large telescopes. So I had to explain to you what is the importance of large and what is a telescope. Now we'll go to how big can we make the telescopes now. Okay. Okay, so let's still be on the lens, which is still very familiar to us. When we say telescope, we always think of a lens. We are still not habituated to talking of a mirror inside a telescope, right? That's not how it is with astronomers though. So this picture is of the world's largest refractor telescope, okay? And it is part of the Yerkes Observatory in the USA. And the diameter of the lens of this is 40 inches, which is 102 centimeters. Can you tell me another name for this kind of a number?
1 meter.
Yeah, so 1 meter, that's right, approximately 1 meter. Just imagine now, just now stop, pause. I was talking about lenses this big, this big. How big is 1 meter? Show me with your hands. Is that big? Is it? Okay. So you know your answer, what you gave now. Go back and check if your meter was that big or not. Okay. So you know a meter is not a small number. And now imagine a lens that big. Okay. I think most of the younger kids will be of that size or that height right now. Just imagine a lens your own height. Okay. And that's part of this telescope, the world's largest refractor telescope. And some slides of my rest of my talk will also dwell on these kinds of records: largest, biggest, widest, etc. Okay, so I hope you like those kinds of things, recording things. Now, just imagine. Now, this is the real picture of the observatory. There's some plane or something going on here, but don't dwell on that. This is inside a dome. Yeah, it's a very cold place. You can see some ice here. This tube that you see here inside, that's the telescope, okay? And then it is housed inside a big observatory. The diameter of this tube is close to 1 meter because that's what holds the lens, okay? And the inside design is like this. So this is the tube, and the diameter of this would be around 1 meter. It holds the lens, and then the light passes here. The focal length is very big. It's about 20 meters, okay? 15 to 20 meters. So just imagine now this telescope has become really big. But when I talk about this telescope, I'll still call it a 1 meter telescope. Okay? Because I have to talk about the primary size first. Right? So it's a 1 meter telescope, but a refractor. Although its focal length can be 20 meters, 30 meters, I don't care. Okay? When I talk about it, I'll call it 1 meter. And you can see it's got like a 5-story or 6-story building inside which it is housed. This is a really advanced observatory, and in fact people cannot really reach here if they are standing here, correct? So they have this platform here which is moved up and down by motors and hydraulic systems, and because you see the telescope, when it goes here, this part comes down here. It's almost like 2 stories down suddenly the telescope is moving. So the astronomer cannot just fly in the air and reach it. So they have a platform which moves with the telescope, and so that the astronomer can keep looking while the telescope is moving down or up. Yeah. So it's quite clever things that people have done for such huge observatories. However, as I said, this being the largest refractor, it's still a very old one. Okay, and in fact, I'll just show you its comparison with some of the largest reflecting telescopes in the world. Okay? And I'll come to details about these, but I'm just showing you the size and the shapes of the insides, the primaries of these large telescopes. And in this, if you can find the Yerkes Observatory, you will see its mirror stands as this blue dot. Okay, that's 1 meter for you on the scale of other telescopes in the world. So don't quickly jump there. Let me take you through quickly through the history. So Yerkes Observatory, 40-inch refractor, was built in 1893, and we've not made bigger lenses after that. So no, stop. It's too challenging. It's too tedious. Let's start going to mirrors. Okay. So as I said, when we say lenses, when we say telescope, even now we think of pirates looking through a telescope and it's got lenses. But astronomers have stopped making big lenses 2 centuries ago, 1.5 centuries ago, right? Now we are making mostly telescopes with mirrors, big mirrors, large telescopes which have huge mirrors, giant mirrors. how giant? So let's see the evolution a little bit. So Yerkes Observatory was in 1993. After that we realized we need big mirror telescopes, and therefore we had the 100-inch telescope, or the Hooker telescope at Mount Wilson, California, built in 1917. Okay, that's about 100 years ago. And this was one of the historic telescopes, one of the first large telescopes built like that in the world, 100-inch reflector. And you might have heard of Hubble. Okay, how come you know Hubble? Sorry?
I know Hubble.
Yeah, so what do you know about Hubble is?
It's a telescope that records things that are out of a galaxy.
Right. So when I say Hubble, you only know of the Hubble Space Telescope. Right? But why is it called Hubble, not Bubble or Gubble?
It was the name of the scientist.
It's in Edwin Hubble.
Edwin Hubble. Yes, Edwin Hubble is the scientist who's honored by naming us the first big space telescope after him. Okay. So Edwin Hubble was a person who used this telescope, the Hooker telescope. And Hooker was the name of another person after whom the telescope was named, which was used by Hubble, and now Hubble himself is famous. And this was the telescope through which the Hubble's law was discovered, and that is why Edwin Hubble is so important in the history of astronomy. Okay, so we had a 100-inch, a few 10 years, 20 years, people carried on with that. They reached the limit saying, okay, now we need bigger, right? And they went for a 200-inch after that, right? Double the size, 4 times the area, and we got a telescope at Mount Palomar called the Hale Telescope, which is 200 inches. However, they noticed that I cannot go on with a Newtonian kind of design, okay, because the length becomes bigger. Newtonians require a longer length, right? And then they went to the Cassegrainian type of design, because there is a folding of light, and instead of flat mirror, the second mirror which was there, instead of a flat mirror, they used a curved mirror to make it even smaller, the cone even smaller, and so it focuses at a closer distance. But for that, of course, they had to make a hole in the center of the mirror. So that's what you see here. The primary mirror had a hole in it. This was the first time they made something like this. So another leap in technology that we get, right? So we get that, and then there were other telescopes being tried out. However, we realized that after 200 inches, it becomes tedious to make a single mirror. 200 inches is huge. Can you imagine 200 inches, how big that would be? Sorry?
5 meters.
Perfect. So 5 meters, it's almost 2.5 times my height or more actually. So that's huge, just the mirror, and having so much glass, grinding it to the perfection, keeping it smooth all the time, moving it because it's got some weight, because now if the glass has increased, it's become as cumbersome as lenses, big lenses also. Right? So making a single glass mirror of bigger and bigger sizes started becoming difficult. Also, how do you transport that kind of a thing? Right? So they used to use railway lines at that time. They didn't have huge trucks and expressways at that time. So they used to use railways, and railway tracks have a certain width. You can't hit another railway coming from the other side. So you can't have two big things being transported. And these things are usually on top of mountains or hills. Right? All of them you'll notice, Mount Palomar, Mount Wilson. So they are on top of high places. You can't transport things there. Then they thought, let's sit down. We want to make bigger telescopes. What can we do? So they came up with another ingenious idea, and that was segmented telescopes. So telescopes in which the primary mirror is made out of small segments, but the complete shape is the same, what we will use for a single mirror. Okay, so they designed it, and they put, let's come to this telescope, which was, or this telescope. This was actually the first time segmented mirrors were tried out in the Keck telescope in around the 90s. Okay, of course, design began much earlier. What they said is, okay, there's no need for a circular mirror. I can have it as a hexagon, I can have a pentagon, whatever I want. I just wanted to reflect light. Sunny ek circle hi hona hai. Yeah. And I want a hole in the center. Again, that is not needed to be a circle. I want it to be big, that's all, right? And shiny and of a proper curvature. That curve is fixed. What focal length it will have will depend on what kind of curve it has. So that has to be fixed. Right. So what they said is, I'll make a hexagonal mirror with that, design it with that curve, and then I'll put smaller hexagons on it, and then make pieces which are like that, of that size, and then later join them together at one place. I'll bring them all individually, then I'll join them together to make the whole big mirror. Okay, and that was tried and it got succeeded. It succeeded in this telescope, which had a leap from this 200 to 200 inch to a 10 meter telescope. Okay. So that was one big leap, and this was not very far off. It was just in the end of last century, 1990s. We got the largest telescope in the world of that time was the Keck telescope, and there was not just one, there were two. So they said, okay, now design is there, so why don't we make two also if we have some extra money in our pockets. So they made two of them, and for a long time this was the largest telescope in the world. However, we have got some more, and I'll come to the names of those very recently, and they're all kind of similar sized. Okay, so they're kind of similar sized telescopes which exist now. These things that you see on this side are planned telescopes. Okay, I'll tell you names and details a little bit later, but these are planned telescopes. And now you can see there's another jump in size, huge jump, right? So this will be a challenge. That's in the next decade, right? That's still these are still not there. These are to come in the next decade. I'll just come to the details of that. But you can see now they are becoming the size of tennis courts and basketball courts. Right? So go and see a tennis court now, and then you'll see a telescope there. So this would be the next challenge. Okay, so instead of showing you just the mirrors, I'll show you some pictures also. So suppose a picture of the sun taken with on such telescope. Okay, so I'll show you the picture of the telescope which uses the largest area. If the workshop people are going away, Sheetal, you can make an announcement that the next session is here.
No, the other courses people.
That's right. Okay, so the largest area used by any telescope right now existing is by the Gran Telescopio Canarias. It's in Spain, in the Canary Islands, and its diameter is 10.4 meters, slightly bigger than Keck. But the area, the way it is distributed, the area is maximum for this telescope. So this is just for some general knowledge or for the quizzing people. These are the Keck telescopes on Mauna Kea Island, Hawaii, and these have the 2 units of 10 meters each. You can see the inside here, the bluish part is the mirror, and then there's a dome over it, and there's this building below it housing all the equipment, etc. Below that, the light goes from here below that, and then there are cameras here inside which take images. And Keck has also given us some of the best and faintest objects in the world. They've made them visible. Then we have one of the important telescopes in the world is actually 4 units. It's called the Very Large Telescope. So this is 4 units of 8.2 meters, and they're separate. And some people actually trying to get their light by optical fibers and combine it at one point and do something called interferometry with that. Okay. But otherwise also, each of these telescopes itself can look in different directions, and at the same site they can give you 4 times the information than one telescope can. But they are slightly smaller, not of 10 meters, but close by. We also have the large binocular telescope, in which both of them look in the same direction. Okay. And that is the largest binocular in the world, and it's again got mirrors of 8.4 meters, 2 of them. You can see the mirrors here, the shiny mirrors. This one has single mirror. It's not a segmented telescope. This one has a single 8 meter mirror. Okay, and you can see now that people are very imaginative when they give names to their telescopes. So they call them very literally what they are. So it's a large binocular telescope. Just also show you the largest solar telescope, because I showed you the picture of the sun. So that's in Kitt Peak, USA, around 1.5 meters in size. And there's a whole building here. The telescope actually diverts light from the sun, cuts it out a lot. Almost 99% of the light is cut out. And then, so here the aim is not to collect more light, but to give more sharpness to the features that you see. So therefore we use the diameter here not to collect light, but so actually we have to collect a lot of light and then cut out a lot of light. But the sharpness increase and the magnification is significant. And that's why we use a huge mirror here. It's the largest solar telescope. And then we have the largest mirror dimension. So this telescope in South Africa, called the Southern African Large Telescope, actually has a diameter of 11 meters on one side, but the other side is 9.8 meters. So things people do for a record. So they have stretched it on one side and squashed it on another side. No, they have not done it to set a world record. There's a specific requirement, technical requirement, because of which the shape is like that. Okay, it is just another beautiful picture of it in the night sky where the Milky Way is seen here. This is a telescope. It's huge actually. And the important part is that India has a contribution in this. So Indian scientists have contributed both money and efforts in this telescope at some time, and now they have a reserved time of around 7% of observation time is reserved for Indian scientists, students, people who want to do research with this telescope. So we have share in the largest mirror dimension telescopes in the world. There's another telescope which is actually a twin of the Southern African Large Telescope. This is also called SALT. If you see the short form, that's a nice short form. Okay, that's the Hobby Evelyn telescope, and what I want you to see is inside it. So that's how the real mirror looks like, not the cartoon image, but it's the real image. Okay, it doesn't have a hole in between. That's another feature of that. You can see here the length is a lot. Here it's a little less. That's the thing. And so it's called a transit telescope, and it uses more area on this side than this side. That's why it's got the largest mirror dimension on one side. You can see people here. People discussing some technical things here, right? So see how small they seem compared to the large telescope. Of course, the telescopes, when you are thinking of them, dreaming of them, it's an astronomer's task to define the science goals. What will you do with the telescope if you make such a huge thing? But then it's another task for a lot of other kind of people to make the telescope itself, right? So the construction of a telescope itself is a huge challenge, and then making it to the precise perfect requirements is a challenge. So I'll just show you a few steps of construction of a telescope. But do keep it in mind that even if you, let's say, want to be associated with astronomy but have chosen a career of being an engineer or software engineer, you can still be associated with an astronomy project and work on building a telescope or running it as well. So construction, of course, as you can see, it requires a lot of mechanical engineers, civil engineers, electrical engineers, electronics engineers, architects, even road planners. So you start with the building. So I'll just show you a place where the very large telescope was built. The first picture was very lovely, nice, because everything is built up. But when it was being built, it was a messy place. And you can see there's it's just like any other construction site in Mumbai that you can see. And the further problems was that this place where it is located is about 700 kilometers from the closest town or city. So you can't go for a chai or something like that. You have to bring your own chai tapri here and make your own stuff. Right. So the road itself had to be made, and they came here. So I'll just show you the process. So they had to come from far off first to find a place. Just imagine people are going 700 kilometers away from a city, just looking at places where it's quite dark and suitable for a telescope. That's called the site survey. Okay. So you need geologists as well for that. then you find a place which is high enough and good enough, and then you make a road to it first. Start from there, so you can take JCBs and make roads, etc. You then have to flatten out the top so that things could be easily built. You start assembling the observatory buildings, some associated buildings, and the structure starts coming up. You have special ways to build the enclosure, or the dome as we can call it. Okay. Then finally the mirror is brought, put it inside. Okay. The dome pieces are brought, put there, and then the mirror is put inside so that it stays covered and it does not get dirty. Okay. And then finally you get the end product, which could be like this. So what I was showing you was a artist's impression of the construction process which will be needed for this world's largest planned telescope, and that is the European Extremely Large Telescope at Paranal, Chile. Chile is a country in South America, and that is going to be around 39 meters in width. Okay. So 4 times the size of Keck telescopes. How big is it? You can see some people and a car here, but maybe this will be more impressive. So you can actually have a aircraft standing inside, or maybe a few of them standing inside the dome. Right? So it's going to be really big. It's going to be, I think, 25 stories high, and this diameter itself is 40 meters. And then around that there is the structure which holds the secondary mirror here, third mirror here. The cameras will be around, and there will be the enclosure and the people who are there. There will be offices. Everything will be there. It's going to be an immense challenge. So that's the world's largest planned one. But I am here to represent the, let's say, you can say the second largest one, and that is the 30-meter telescope. And it's especially important to us because it is a project in which India is a partner. Okay? Indian partnership is again around 10% in that, and we are going to make it of 30 meters. The other telescope is in the southern hemisphere. This one is in the northern hemisphere, right? On the islands of Hawaii. So this is a picture of. I find this very strange and very exotic because this is an island. This is called the Big Island in Hawaii, and the mountain here is called Mauna Kea. Now just imagine there's beaches here where people go for scuba diving and surfing, and then there's place right here where people can go for mountaineering and look at ice there, right? What a contrast! You have the Himalaya and Goa at the same place on the same island, right? And it's not a very big island. It's called big, but I think it might be some 100 kilometers across. That's all, right? It's an amazing place, and this also happens to be a sacred location for the people there. So they consider it to be the place of the goddess of the island. It's also a sacred location for astronomers. Why? Because this mountain here, from the sea level, the top is 4 kilometers. 4 kilometers upwards. Okay, and so because of that, it gives you one of the best sites in the world for astronomy. Right? So there is no other site which is that high and devoid of any kind of human intervention close by. Also, since you are that high, you are basically above cloud levels. You see the clouds are below you here. There's a second layer of cloud. It's also actually below this level of these observatories. So 13 international telescopes exist on the mountain's top right now. 13. So you can imagine, yes, it is one of the best sites in the world, including the Keck telescopes that I was talking about. These two spherical domes, I just love them because I spent my childhood wondering about them. But then there are, of course, other smaller and comparable telescopes on there. And that's where, close by on this side, we'll hope to have the 30-meter telescope built in the next decade coming up. It's another picture because I wanted to show you that even a thick layer of clouds below does not hamper observation of the lovely sky up there. Right? And this is ice here. So as you can see, it gets really cold, and that actually gives us better conditions for astronomy compared to a hot place. Okay, so hot, dusty is something we don't want. Alright, so that's Mauna Kea, and as I said, that is the best site in the thing. There are other sites. The second best would be the Paranal Chile, where the very large telescope is there, and you can see lovely sky. And it's also important because it's in the southern hemisphere. So you will realize that the Earth is curved, right? And so if you are here and looking in this direction with telescopes, you can probably see in this direction only. You can never see objects which are in this direction because the Earth is stopping you. Right? So if you go to southern hemisphere, then you can see the objects on the opposite side. Right? So it is important to have big telescopes in both the hemispheres. And so I think it's a lovely thing that in the next decade we are planning the 30-meter telescope and the extremely large telescope as well. Okay. And both of these will have something called adaptive optics, which is a which I'll not go too much into, but you might have noticed this laser going out from the telescope in some of the images. Right? You might wonder why the laser is going out instead of light coming into the telescope. So this is part of something called adaptive optics technology. I don't have much time right now to explain or go into details of that, but what we basically are trying to do is to eliminate the twinkle twinkle out of the star. Okay, we find it lovely, beautiful that stars twinkle at night and it's very romantic or whatever, but for astronomers it's terrible. Why? Because we actually want to get a picture of the star. Now just imagine you're telling your friend, I want to take a selfie with you, and the friend keeps moving like this all the time. That will be a nuisance, right? And that's what we are trying to do. Normally somebody moving like this might be a good dance to see, but when you want to take a picture of them and keep it, it's not a good thing. So how do you remove that? So what we do is, so your friend is moving, we try to move the camera along with them. Now if it's a random movement, then it will be difficult to track them. Right? My camera can, but if I know that it's a particular kind of a dance which is happening, right, then I can probably imagine what is going to be the next move and move the camera accordingly. Right? So I can program my movements. So just this is a very this is just an example of what adaptive optics does. So what we are trying to do is here we are trying to look at stars up there, let's say, and other things which are faint. And the problem is not that the stars are moving around. The problem is the air in between is moving around, right? And the air itself is like a lens. Okay? You may not feel like that in daily life because tiny changes in something won't make your friends look like they're twinkling. But at night, when you think you have clear skies, there's still some wind going on, okay? And it is changing the density of the lens which is in between us and the stars. Okay, it's the atmosphere, and these can cause tiny fluctuations, and you call them tiny, but you can actually see that the stars seem to be twinkling on some days when it's windy, and they twinkle less on some other days when it's not so windy. Okay, now what we do is we use this laser here, and we create an artificial star right at the end of our own atmosphere. Okay, there is a layer of what is called sodium ions. Okay, sodium, this element. Okay, so sodium ions are there, and they actually reflect this yellow kind of light. So if you shoot a yellow laser, it will reflect it back. Okay. That's a very strange thing we found only with the help of meteorologists. So a lot of partnerships are needed to be done by astronomers, and so that reflects the light. So what we do is we shoot a very tiny thin laser at that layer, and what we get back is a shining bright dot there. Okay, and that is a star. It's like a star. It's a tiny bright dot at a very high height. Now what is special about this star is that I have made it. We have made it. It's an artificial star. We have made it. So we know all properties of it. We shoot the laser, so we know where it should be. Right? And now what I do is I make that artificial star near the object that I want to actually see. The star or galaxy that I want to see. So I make the artificial star because I have the laser, I can point it in any direction. I make it close to that object and I take a picture. I take a photograph. Okay. In that photograph, since I have shot the laser, I know where the point should be, the artificial star should be. However, the air is moving, so it changes the position of the star. Okay, artificial star. That gives me information that I am expecting the star to be here, but it's actually here. Right? So what I know now is that the air has changed any point which was here to here. Of course, that will apply to all the other points in the same picture, right? So then what I can do is I can change all the other points also by that much amount and get a cancellation. And then I keep taking these pictures, adding them up, and I get a beautiful steady image. Okay, so that's one way to do it. The other way that astronomers with adaptive optics are doing are that they are there's not much detail. So they are using some technology which actually changes the shape of the mirror a little bit. So rather than moving it in the image, like I take a photograph and then move the photograph a little and move all the photographs slowly and then combining together, what I do is I change the shape of the mirror a little bit, so that the focus which was changed due to the atmosphere gets corrected for, and I use the same camera and the same frame is there, but I don't have to move images around. So that's called adaptive optics, in which I adapt to the change in the atmosphere. And as I said, we make an artificial star for that, and then see the changes in that star and apply it to our telescope. Well, there's quite advanced stuff which has happened over the last century, and this is definitely something beyond our understanding of Galileo. But yes, because of all these things, in which India is also a big role player. So you can see this is something called Robo Adaptive Optics, RoboAO, which the institute which I work on in IUCA in Pune has actually developed. This is the technology which we have developed, and it's now being used by telescopes across the world, okay? Including this telescope in the USA. So adaptive optics is another thing which large telescopes have now. So two important things are this big mirrors and adaptive optics. And what would it allow us to do? So just an artist impression now. If you look at a patch of the sky with the 30-meter telescope, let's say, okay, and we are seeing something like this. This is without your adaptive optics switch being on, right? So now you say, okay, switch on the adaptive optics, and you can get clarity like this. So this is an actual simulation of it. I'm not just showing random pictures. So this has been calculated that what kind of effect the adaptive optics system will give compared to a non-adaptive optics system like this, right? So here, yeah, you can find out details like this is a circle, it's a blue circle, there might be something, some spotty things here, right? But this is what you might get with the adaptive optics on. Amazing, right? So why I'm showing you this picture is because I just wanted also you to know about the objects that the 30-meter telescope will study. In brief, I'll tell them, and then you can go to the exhibition and know more about them from the panels. So the main science objectives of the 30-meter telescope would be studying the formation of stars and planets, including those in our solar system, looking at the nature of extrasolar planets, which are planets outside our solar system, planets going around other stars. Okay. Amazing, we are now thinking of other stars and their planets, presence of life elsewhere in the universe. So when you're talking about other bodies, other planets elsewhere in the universe, of course we will also look for things which are living, which may also be intelligent like us. We don't know. We would of course like to go beyond that and go for the rest of the universe beyond our galaxy and go for the formation of the first stars and galaxies, and also the nature and the composition of the universe now. Right? These are two separate eras that we will study in the universe. So as I was saying, our solar system itself is quite unexplored till now, and we have this inner system which we mostly know about. The picture I was showing you with the blue dots, that's somewhere in the outer solar system here, and there's a huge belt of tiny objects outside, or sorry, rather just outside Neptune's orbit, and this is called the Kuiper belt. This is an area we would love to study, and there are objects being found outside, and they may even have the what is called the 9th planet or the 10th planet hiding somewhere, right? So we still want to look at that. Now the thing is that now we'll get extreme clarity about these objects, and things which were very faint and blurry till now would be clear, and also things which were clear till now, we will be able to monitor them. Like we can monitor the atmospheric conditions on one of the satellites of Jupiter. Right? We can go to that kind of accuracy. We will look at other stars. Anybody recognizes this picture from somewhere? Any sci-fi interested people?
Supermoon or something?
Supermoon, igloo. The hint is sci-fi, science fiction. Movie. It's not a real picture, of course. No. This could be a picture of a planet which is going around 2 stars. So instead of having something like the sun, it has 2 stars. One is a cooler star, one is a hotter star, and the planet goes around the center of gravity of both of them. Right? So, and still no answers to this.
Star Wars.
Sorry, who's that?
Star Wars.
Star Wars. Can you name the planet? Then I'll give you a goodie bag. Or this character at least. No? Okay. So that's from Star Wars, and the planet was called Tatooine, and this is Anakin Skywalker, who later becomes Darth Vader. Oh no, sorry, this is not Anakin Skywalker, it's his son. So this is from the first Star Wars movie. Right? So have a look, those are interesting movies, but what I'm saying is that these kind of planets may actually exist, right? And we will be able to discover them, we will be able to study them in detail, and we can do a lot of scientific analysis of what they may be like. Do they have atmospheres? What is their composition? Are there organic molecules? And are they present everywhere? Are we very unique or not? Or we just, one of the life forms of which many of them exist, right? Then we also look at galaxies far off. Again, maybe something like Star Wars. So this is a picture which the Hubble Space Telescope had taken, and this is kind of the best pictures that we have got of the faraway universe. And of course, in that there are galaxies here. And this one is a star. In this whole picture, everything is a galaxy. This one is the only star. Right? It's that powerful that you can see a tiny area, and that area has only one star, and all others are galaxies. Okay, and of course there are bigger galaxies that can be studied in much detail, and of course there will be tiny things, blotches, which are blotches for Hubble even, being there in space. These will become clearer. These might start looking like these. Okay, and now imagine having billions of these galaxies, and us doing surveys of the sky, us getting clear information about these galaxies, the red ones, which are the first ones forming in the universe 13 billion years ago, 14 billion years ago, right? And the light has traveled so long to get to us, and now we will finally be able to get the details of these galaxies with the large telescopes coming up in the next decade. So that's what we'll have. I, of course, cannot stop without mentioning that we may be sending telescopes to space. Okay, there's the James Webb Space Telescope coming up, which I don't have a picture of right now. I do have a picture of Hubble Telescope, which was the most famous and went to space and has given us some of the best images of the universe till now. We will probably struggle a lot. Maybe it will be next century before we put a 30-meter telescope in the space, but at least now we'll have it on the ground, and which will give us a lot of details. So with that, I conclude my talk about telescopes, the large telescopes of the world, and hope that you are inspired, and maybe some of you will want to contribute to these projects as well. Thank you.
questions are there, you can ask.
Yes, thank you.
And Samir, if you can just give some more idea about careers in astronomy just in 5 minutes.
Okay, I can do it. Yes. If the audience is going to be sitting here and is not going to wishing to go away somewhere, then I can of course spend a little more time on that.
Questions if they have.
Yeah. So if you have any questions, please go ahead and ask them.
If you can please answer the same questions here.
I'll do that, yes.
Anybody else having any questions specific about today's talk, telescope, or anything about astronomy?
So if you don't ask questions, I will ask few questions also. But let me delay that a little bit and tell you a little about what can you do if you are interested in astronomy and are so interested that you would like to go for a research career. Okay. As I said, astronomy is not only done by astronomers. You can also contribute to astronomy projects, being an engineer or a software person also right now. Okay, but that is still a little peripheral. You can become an astronomer also if you. I mean, there are people who have left software jobs and have actually become well-known astronomers in the world. So it's up to your talent, how you adapt and how you quickly gain knowledge of things. But what do you do to get to become a regular astronomer, of whom there are many in India? The best possible path for that, I suggest, is going through a bachelor's and master's degree in physics, okay, or mathematics if you are more interested in theoretical astrophysics, as it is called. So this is a path which will give you the best knowledge, overall knowledge of physics, of which astronomy and astrophysics is a part. Okay, but then there are also options where you can directly go for a bachelor's or master's in astrophysics. Right? It could be in India or abroad. Mostly abroad. India has very less number of astrophysics courses at truly completely astrophysics courses at master's level. This would be, I think, some for BSc you might all have to wait for around 5-6 more years to get to a BSc, and to get it 3 more years, and then masters would be 2 more years. So a lot of years of fun studying for you to become or start becoming a researcher. Okay, and you have to keep it fun yourself over all these years. So after you do your masters, either in physics or astrophysics or mathematics, we suggest that you join a research institute as a PhD student, as a person who has joined for a PhD research project. Okay, there are again several institutes in India and abroad where you can join for this, and you will be able to choose from choose objects to study, right from things like the sun itself, which is very close by and very enigmatic. So a lot of things happen in it. You could choose to look at stars, close by, far off, in clusters, single, small, big, colored, etc. Okay, and star clusters like the star cluster here. You could choose to look at dead stars, which are there in the form of nebulae. Yeah, you could or you could choose to look at galaxies, and you could choose to look farther away than the closest galaxy. This is Andromeda, of course, but you could go and look at things really far away also. Okay, using the other telescopes. So these are the kind of topics that you will choose at your PhD level, and you will spend anywhere from 3 to 5 or 7, sometimes if the project is it's long drawn. So in that you will get research experience, and that's actually at that time you're already a person paid to do astronomy, right? Because how much fun is being paid to do what you love doing, right? So that's the level when you're actually starting serious research, And after your PhD, of course, you're a doctorate, and you'll have to start your career as a faculty somewhere, as a professor, researcher in, again, many institutes which exist across India and the world. Amongst Indian institutes, I would name a few that are leading, and that includes the Indian Institute of Astrophysics, which is the largest institute for this. It is in Bangalore, and one of the oldest astronomy research institutes in India. It's also got facilities across India. So there's the Vairi Bapu Telescope in Kavalur in Tamil Nadu. There's Kodaikanal Solar Observatory, and then there's the Hanle Chandra Telescope up there in Leh, Ladakh. Okay. Then we have the Inter-University Center for Astronomy and Astrophysics, which is very close by in Pune, where we have actually come from. So it also has a 2-meter class telescope, but then other than that, as I said, the Southern African Large Telescope has an Indian contribution, right? So that partnership is through IUCA. Also, IUCA is part of the 30-meter telescope project in collaboration with the Indian Institute of Astrophysics, and in collaboration with ARIES, which is the third partner, let's say third big partner for TMT. This is in Nainital, and it's another observational astronomy institute, and very famous for the results it has got till now. It is actually in charge of a telescope whose picture I don't have. It's a 3.6 meter telescope, so that's the biggest one in India right now, and it exists close to Nainital at a place called Devasthal. So there are observing facilities in India, there are institutes in India, there are institutes like Udaipur Solar Observatory, which is sun-related observatory, very different kind of approach. So all these places are there for you to study at and do research for, but of course there will be a regular, competitive path to go through. You have to get through your master's degree, and preferably in physics, because then you get an overall view and you can use other aspects of physics in your astrophysics research, right? As research is a lot of collaborations, and then if you just restrict yourself to saying, okay, I will study only discolored galaxies, you will not make any friends then, because the other people, you will not talk to any other people. So it's better to diversify your research interests and study physics for your masters, go for a PhD degree, get it, and then start the career as an astrophysicist. All these places exist, and for masters also there are very nice institutes like ISER, the Indian Institute of Science, Education and Technology. So that's something you should consider after your 12th also, other than the IITs that everybody prepares for. But if you have an inclination towards science, I would suggest places like ISER Pune, which are excellent places, and they have teachers who are good. That's most important thing when you are choosing a place to study. The teachers should be good. It should not just be, oh, wow, what a building, or it's 100-year-old building or something like that. No, or they have large screen projectors or computers. No, the teachers should be good, and that's why I recommend ISES, because the teachers there are themselves researchers. So they're not teachers who might be doing research once in a while. They're researchers who have come to teaching and come back to India sometimes from abroad. So I think these are very good options. ISERs. There's also NICERs in all states. We are starting to have NICERs, IITs, and of course reputed colleges. I have very good volunteers at the TMT booth who have come from renowned colleges in the city here itself, St. Xavier's, Ruparali. So you can talk to them, go to the exhibition, you can ask them which are the best colleges they found, and they can also help you. So I think that's good enough advice.
Okay, any questions you have?
So I have a question. You spoke about adaptive optics, where you said that whenever you see any obstacle or any hurdle, you all shoot the laser beam and you all create an artificial star so that you can study a particular heavenly object. What happens in a condition where you have these two stars which revolve around each other, and you want to study it with a lot of clarity, and you see them in movement? So how do you study them using adaptive optics, because they're both moving and you want to see them clearly.
Okay. So adaptive optics is used only to remove the effects of the atmosphere, nothing else. And this removal of the effect will apply to anything we study, be it a faint galaxy or stars, binary stars. It should not change anything in any way except the atmosphere, except for removing the atmospheric effect. So that's all we do with the adaptive optics. So adaptive optics changes the shape of the mirror, so we get a constant image. Rest of that is the study is the same as any other way. Okay. So particularly if you are asking about binary stars revolving around each other, so they don't revolve at very fast rates. And if they do, stars themselves, there are no stars which we see revolving within seconds at optical wavelengths, which TMT etc. studies, right? There are stars which revolve very fast. These are neutron stars, not normal stars. But they don't emit light, normal light. They emit radio light. And there are telescopes like the GMRT, the radio telescopes in the world, which can see them, but they have no atmospheric thing to correct for. So they have their own ways of doing it. I think, so we don't do anything specially for binary stars separately with adaptive optics. It's just to cancel out the effect, whichever object it is. Yes, please.
So you be interested in a particular event or regular you observe the planet, galaxy and other stars, and
Okay.
in this climate conditions matter in your observatory?
Yes, definitely climate conditions matter. So as I showed you this place, it does have weather conditions, and although it's above 2 layers of clouds, there can be a third layer of clouds which come up. And so when it's bad weather, we shut the observatory. Simple as that. Optical observatories always have this problem. We have to have certain number of nights a year, and then we choose a site which has the best number of nights over the last 100 years. We take the geological, meteorological record and choose a site like that. So yes, climate affects it. The Ayuka Giravali Observatory is very near Pune, and it closes in the rainy season. It's closed for 3 months. We can't help it. But while we are using it, the precious 100 nights or 200 nights that we get, 200 nights is a big deal. Okay, so those precious nights that we get are distributed to people who put forth proposals. So these are scientists, researchers who can apply to the telescope saying, I have this kind of study to do. I want to study this part of the solar system and try to find the 9th planet. Okay, so of course I cannot give them time for 100 nights. All to them, because nobody else will do any research. So what they are given is, let's say you want to find the planet, you'll be given 5 minutes on these 5 nights over this month. You take a picture of your favorite area where you want to find, you take that image, go home, study it, right? And that's why nobody actually looks through telescopes like this. That's something which I should also clear, that these large telescopes, nobody looks with their eye, there's no eyepiece there. Okay. All of these have directly cameras. So every precious second that is spent using these telescopes is recorded somewhere. All of these data, of course, has something that the researcher wanted to study, but they may have details which nobody wanted to study, but it is there. The discovery potential is also there. You want to study and find the planet there, but there might be a new comet which has come into that frame, which you are not looking for, and you may not also look for. So after a few years, this data is made public. Okay, what does it mean? Even public can look at it. Of course, if you have the expertise and you know what to look for, you can actually also look at all these data, right? And so then that is when discoveries from previous data happen. Okay. So hope that answers your question, that not everybody looks at them all the time, but people actually have to compete, and they have to put in good proposals asking for this precious time. And that's how it is distributed. Yes.
One thing I would like to ask, so can somebody go and visit this Pune Ayuka Center?
Ayuka, yes, Ayuka is based in Pune, and we welcome people. Particularly on Thursday afternoons, we have public visits inside the center. We give you information about it, and you're taken around for about 1.5 hours, and you'll get a good view of it.
So on your
The observatory, however, is not in Pune. It's at a remote place, so we don't have visitors going there so much.
Do we need to do some sort of formatting?
Yes, so you just look up Google and look up Ayuka visits on Google, and you'll get all the details there, there's contact details, etc.
Yesterday I had spoken to you about visitations to these laboratories and these observatories, and you
yes.
very rightly justified why visitors are not entertained and justifiably so. Now we have children who are in that stage of curiosity of knowing their galaxy and all these things. So which would you recommend for students to visit?
Amongst observatories, I think most of them are not so easy to reach. That's one of the reasons why I don't prescribe you. But then all observatories, they try to have a visitor center, where if you go there, there'll be somebody special waiting to tell you more information. They'll show you images taken with the telescope. Now, a telescope, like if you let's say look at Qutub Minar or something like that, right? So it's got a grand aura and things like that. You say wow when you go there, but then after that next day, just by looking at it, you don't get anything more, right? However, if I have a chapter on the Qutub Minar or a nice book on it, I can read more details, etc. Or if I have a visitor center there, I can get more information and it could be useful. So most observatories also have visitor centers which you could visit. However, they do take out time, and if you write to them, they might allow you to make a visit sometime. But that is not highly encouraged because it's not about security, but it's more about the convenience, because the staff there is kind of limited. It's not they have a big staff there, and they have particular tasks to carry out every time, because they have to get the observatory ready for the next night, etc. Right? But many observatories, like Ayuka Center, is not the observatory you were mentioning. So observatory is at a different place. But there's the giant meter wave radio telescope, which is close by again to Pune, the GMRT, and this is a place you could visit. And they do have observatory visits on Fridays. So again, look this up online, GMRT or visit, and you can actually book a slot there. This is something I would recommend if you are here close by for you to visit.
It's nearby Pune, sir?
It's near Pune, yeah, around 80 kilometers from Pune. It's also, if you go through Nashik, then it's before Pune for you from Mumbai.
Via Nashik.
Sorry?
Via Nashik.
If you go via Nashik, it's on the Pune-Nashik highway.
I have a question to ask.
Sorry?
I have a question to ask.
Okay.
What if I don't like physics, studying physics, and I like chemistry, biology, or computers? Is there anything for me to do in astronomy?
Yes, of course. Okay. So astronomy is the word, means studying the sky. Okay. So we sometimes say, okay, if I don't want to study the sky, I'm interested in biology. Is there anything to do for me? Well, if you are interested in research in biology, and then you are interested in biology of things elsewhere, yes, there are fields, subfields of astronomy, which are like astrochemistry, astrobiology, where you can also pursue a research. Right? You will be probably using the same knowledge of biology or chemistry that you got during your masters in biology, chemistry, zoology, geology even. Okay, there's also something called planetary geology. So these are the kind of knowledge that you will use to astronomical objects. Okay, so when I say I will be looking for signs of life on other planets around other stars, it will definitely require me to talk to a chemistry person, who says, okay, this is the sign of life. So you need to have acetaldehyde or something like that, right? So DNA ka structure kaisa hai, or what is the spectrum of that, right? And it's a cross-border thing. So when I'm talking about DNA, I'm also talking to a chemistry person, I'm also talking to a biology person. So yes, there are fields called astronomy, astrobiology, astrochemistry, planetary geology, because I just want to find out what is the surface features on Titan, let's say, which is a satellite of Saturn. So I have to talk to geologists about that. And in the future, of course, people may be actually traveling to these places. That's quite a bit away, but yes, there will be options where you can be from other sciences and still be associated with projects which have outer space in them. So, okay. Some question, please.
गेल्या 100 वर्षापासून रिसर्च चालू आहे. सायन्टिस्ट ते वर्क ऑलरेडी. आता तुम्ही जसं सांगितलं की BSc करून नंतर PhD करून मग ते रिसर्च वगैरे म्हणजे मेबी टेक 10 more than 10 years. तर पुढच्या 10 वर्षांचा काही स्कोप आहे का? म्हणजे जर हे स्टुडंट आता जे 10 वर्षांनंतर
आता मी तुमच्यासमोर हे प्रोजेक्ट्स जे मांडले आहेत, all of these are just starting now and they will be primed say 7 to 8 or 10 years from now. That is the time when they will require these PhD students to research. तर आत्ताच्या स्टुडंटसाठी हे ॲक्च्युली चांगली वेळ आहे. जर त्यांना आतापासून त्याची माहिती असली तर पुढल्या दशकात ते त्यासाठी तयार असतील, ती फॅसिलिटी वापरण्यासाठी तयार असतील. आणि त्यामुळेच आम्हाला असं वाटलं की आता ही एक्झिबिशन करावी. म्हणजे दिस इज द प्राईम टाइम दॅट वी कॅच देम यंग अँड inspire them for the project in the future. Of course, it is not that it will finish there. The observatories themselves are made with a lifetime in mind. तर 30-meter telescope जरी समजा 2030 मध्ये सुरू झाला, for example. So it has a lifetime, of course. So it will run for the next 50 years, and somebody or the other will have to make use of it. So yes, there is a lot of scopes. People will keep changing and students can join them. सो मी तुम्हाला काही एरियाज सांगितलेत की या टॉपिकवरती ते काम करतात. सूर्य असो, तारे असो, गॅलेक्सीज असो. आणि ते त्यांचे एकतर ते त्यांचे इमेजेस घेतात, बेस्ट क्वालिटी इमेजेस घेऊन त्याचे स्ट्रक्चर काय आहे, त्याच्यामध्ये कसे बदल होतात, त्यांची हिस्ट्री कशी होती, फ्युचर कसं असू शकेल हे ते निर्धारित करतात. आणि त्याशिवाय जवळच्या वस्तू ज्या आहेत त्याच्यामध्ये बदल अजून वेगाने होतात, ते आपण बघत असतो. नवीन वस्तू काही आहेत का जे आपल्याला आतापर्यंत माहिती नाही, त्यांच्याविषयी माहिती, त्यांचा ते याच इमेजेसमध्ये शोध करतात. ऑफकोर्स त्यांचं उद्देश म्हणजे अजून सापडलेली नाही वस्तू इथे असू शकते असं माहिती असून मग ते शोध करतात कधी कधी. आणि कधी कधी न माहिती असताना देखील एखादा शोध लागतो. तर असे वेगवेगळ्या प्रकारे शास्त्रज्ञ काम करतात. म्हणजे मी कम्प्लिटली ऑफकोर्स प्रत्येकाचे एक्झॅक्ट डिटेल्स काय काय हे सांगणं जरा कठीण जातं, पण मोस्टली ते आपल्या दुर्बिणीतनं घेतलेले जे चित्र आहेत त्याच्यावर आधारित करून काहीतरी त्यांचं रिसर्च गोल ऑलरेडी असतो की मी याची प्रॉपर्टीज काय आहेत ते शोधणार जाणून घेणार. आणि मग त्यातून अजून काही माहिती मिळते का. म्हणजे समजा मी या अंतरावरच्या सर्व गॅलेक्सीज बघितल्या आणि त्याच्यामध्ये सर्वांचा आकार सारखाच आहे, मग तो प्रश्न पडतोय का सारखा आहे. असं एक्झाम्पल देते, असं नाही आहे. तर किंवा या सर्व गॅलेक्सीज एकाच वेगाने आपल्यापासून लांब जात आहेत, तर याचा अर्थ काय. त्या गॅलेक्सीज बघितल्यानंतर ते आपल्याला कळतं, आधीच आपल्याला कळलेलं नव्हतं. असे बरेच उदाहरण आहेत या प्रकारे शास्त्रज्ञ काम करतात.
Okay, so I think we'll conclude this session. Thank you so much, Samida. You have given very nice, insightful information to all of us. So I would like to say thank you from all of you, and please give a big round of applause.
We have another session here
We'll
after
have
break.
this for kids. Kids will be going to the class. All those like from current class and the previous class, they'll be having telescope making session. Parents can actually enjoy the exhibition which is there at the main gate. 2 o'clock we'll be meeting here for the Galileo play which Samilda has already mentioned. So 2 o'clock we'll start it. Okay. So we'll conclude the session.
Okay, so just before concluding, we want to, of course, we have some goodie bags here from the 30-meter telescope, and we want to not just give them away, but I want you to do some work before that. So one goodie bag definitely goes to the first question that you answered here, which I've reserved for you. So I have, let me ask you a few questions based on the talks, and then you can stake a claim on the goodie bag. Those who were here yesterday, please do not participate in the competition. And their friends and relatives are not allowed or something like that. No, just kidding. So I will just randomly ask some questions and see if you can remember some part of the talk. Okay. Alright, some maybe as easy as asking you which is the telescope which has the largest area used in the world. From the talk I told you, and if you remember the exact name, see I won't make it very easy, but because there's a goodie bag. So okay.
Paranal Chile.
No. Which is the telescope that uses the largest area? Hint, that is the first telescope that I showed. I am talking about things which are there existing now. No sir, this is this is the radio telescope. I was talking about the telescopes in the talk, and if you were here earlier, I had actually these badges for the large ones. Okay, let her try first. Grand telescope. Where is it? That's an important part of the. Do you have a better answer?
Keck telescope.
No, it's not the Keck. Anybody else? Yes?
Hubble telescope.
No, Hubble is actually quite small. Hubble is a 2-meter class telescope. So what I am talking about is a 10-meter class telescope. Yes, please.
I think it's in Spain.
Okay.
Grand Telescope, Canary, something like that.
Alright, okay. So since she is giving a more complete answer, I will give you the prize. Yes, it is the Gran Telescopio Canarias. That's a Spanish way of saying the Grand Telescope at the Canary Islands in Spain. Yes, and that's the third best site in the world for astronomy, I would say. Now the other question is, what is the second best site in the world for astronomy? Okay, you can answer. Mauna Kea is not the right answer. What is the question? The second best site in the world for astronomy. Just I told you this is the third best. Okay, you can try. Chile is a country, it's a huge country like India. So what is the place?
Paranal Chile.
Please raise your hand, I'll ask you, then if you give out the answer then I cannot give you the goodie bag, so I will keep it myself. Okay, I'll give you a chance. No, that's not it. Okay, you can try.
Paranal Chile.
Okay, fine. So let me give him, because he's younger than you, so I'll give him the answer. So Paranal Chile, yes, that is the second best site. Well, when I say second best site and all that, don't take it too badly and say I will not go ever to Paranal because it's the second best. It's still great, excellent site. It will actually have the largest telescope in the world at some point. Optical telescope. Okay. Now, a question which has two parts, and if you answer both of them right, then you'll get a goodie bag. What are the two important features of the 30-meter telescope which make it unique and one of the best in the world? Two important features. Two important technologies, two important unique things. Let others try. You already got one. Yes.
The adaptive optics and then the segmented mirrors.
You were not there yesterday. Alright, so that's a very prompt and nicely studied answer. Yes, the important things which set the 30-meter telescope as a new next century device is the huge 30-meter multi-segmented mirror. And earlier telescopes would have, let's say, 30 segments or so. This one will have 500 segments, 492 to be precise. Each of them will be 1.4 meters in height. Just imagine now this huge coverage of that. And of course, they will all be able to move slightly up and down to correct for the atmosphere above them, up to the limit of 4 nanometers. Okay, you can move these huge mirrors by 4 nanometers if required, as little as that. Okay, and so that's the other unique feature which is inbuilt there. So multi-segmented mirrors and adaptive optics is the correct answer to that. Okay, so I think that finishes all the questions that I can ask and the most information that I can give you about the projects and large telescopes. Thank you for being here. You can get in touch with us. The email ID, I'll leave it on here. And please do come back for the 2 o'clock session. And the kids can now follow Sheetal, those who are in the workshop.